Okay, yeah. So this is kind of a short section. So I do know we didn't do part 2 and 3, and you're not off the hook. We're going to have to go back and pick those up. But those are a little bit standalone, and I like 2 and 3. I've done this before. They kind of wrap back around to something else we earlier talked about. But I want to do part 7 and then get into part 8. So part 7 is percent yield. And I went out on the internet again today to see if I can find what I grabbed. And it's all about brownies at this semester. I do not know why. Okay, so this is a different brownie recipe because I wanted a brownie recipe that had, oh, forget the sound effects, so it's just kind of frozen on there. I wanted a brownie recipe that had this word right here, yield. Okay? So you would tell me if I mix, and it's kind of lopped off, but if I mix 4 eggs, 1 1/4 cup of double Dutch dark cocoa, okay, this amount of salt, this baking powder, etc. If I do all of that, that's in the right stoichiometric ratio amounts, okay, I will make myself 2 dozen brownies. That's my yield. So we said that the ingredients are like your R's. What does R stand for? Reactants, very good. And the yield is like, your brownies are like your P. Products, yep. So R goes to form P. Shorthand notation for a chemical reaction. So when we talk about yields, we're focusing on brownie yields. No, we're focusing on the products. Okay, so percent yields. How much product did you get back? So the yields, actually, we oftentimes have 2 numbers. We have the number that you came up with the stoichiometric calculation. So I know it probably says this in this slide, but theoretical yield, that is from, FR for from, stoich, S-T-O-I-C-H, calc. Okay, where do you get your theoretical yields? You get them from your stoichiometric calculations. You guys have been doing theoretical yields anytime you went from the mass of a reactant to the mass of a product. Those are theoretical yields. It's wonderful. Okay? That's easy. And the other one's not too bad either. So I want to digress a little bit. So those of you who are test watchers, like, will she put this on the test? Blah, 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 blah. I need to put some word stuff on the test in addition to the number stuff on the test that's going to be at the end of your test.
Yes, please do.
It'll be a balance. Okay. No worries. So my point is that these are some kind of cool concepts, I think, but that's just me, to kind of say, well, if you do a chemical reaction and if you start with X amount of ingredients, reactants, why don't you get Y amount of product? Why don't you get that mass you think you should get? Okay, and usually, actually, these are all biased. If you're familiar with the term bias, these are all biased low. Why don't we get what we thought we should get? Why is it always a little bit lower than usual?
They cut them too big.
What's that? They cut them too big. That's right. Exactly. And I'm going to talk about each one of these, okay? The first 2, if you want to write Chem 2, actually, we're going to be covering these in Gen Chem 2. CHM2. So why wouldn't you get back what you thought you should get back? Now, I like this one. For us who are impatient, reaction kinetics, okay? So how long does it take for A to go to form B, for R to go to form P? How long does that take? Do we have the patience to wait for those brownies to cook? Okay. Now, we assume a lot of chemical reactions go just like that. When your reactants combine, they proceed to form products. But that's not always the case. We're going to be talking about something called reaction rates, okay, in Chem 2. So in other words, if you pull it too soon, I think of kind of developing film, the old-timey, if you pull it too soon, you don't get your picture. If you pull it too soon, you only have partially converted your reactants to products. So that's why it's always low. And this is actually showing you a little bit of reaction rates. The red up there, you kind of see it going down along the x-axis. Kind of get used to these in Gen Chem 2. But along the x-axis is time. Along the y-axis is the amount you have left. So you can see the red is decreasing. Actually, that's our reactants. You see the P is increasing. That's our product. Okay? So it took a little bit of time. And actually, to me, even here at 30 seconds, does it look like we still have a little bit of our reactant left in go-to-form product? And as some of you know, we can actually get a sense for how it's changing if we take a line tangent to that curve. We'll talk about that a little bit in Gen Chem 2. So reaction rates. So we pull it too soon. It hasn't reacted. Here's another one. I like this one too. This one is like, you're just never going to get there. We're used to, in Chem 1, we do a lot of this. I do an R goes to form P. Reactants go to form products. That is awesome. And we aren't even going to worry about how long it takes. Okay, but there are a lot of chemical reactions out there that not only do they say, we say go from left to right, but they also go from right back to left again. Notice I drew another arrow in there. So you're like, dude, some of it goes to form products, but the products actually go back to form reactants. So it's kind of a seesaw-y back and forth. It's in what we say dynamic equilibrium. So when you isolate this guy, it's never going to be completely converting all of our R to P. So it's kind of a little bit of a moving target. And up at the top there, you see an example of a chemical equilibrium. It just is. It just is. And it has to do with energy and the compounds that are involved as reactants and products. Okay. So this is kind of fun. Now, again, we read it similar to the one before. So along the x-axis is time. So this is time 0 over here. Time ticks off, ticks off, ticks off, ticks off. So the way this kind of reaction is showing you, you buy this, that how much, oh, by the way, we'll run into this soon. Anytime you see this bracket, so you see HI in brackets, anytime you see bracket, that means molar concentration. We're going to get to that today. That's molarity. Molarity. Basically, it's how concentrated that is. So does this make sense? At time 0, T is equal to 0, ground 0. At time 0, the molar concentration of HI is 0. Molar concentration of the two reactants as they're written here, if we go from left to right, okay, the two reactants is some number, doesn't have a number there. Okay, you let her loose, and then it starts to go ahead, and in this case, assemble HI units over on the product side. Okay. Let me see. I'm going to pick another time. Do you see about, I'm going to try to kind of pick a time about that time. About that time and later. Doesn't it kind of look like you've basically reached the amount of HI that's going to form, and you've reached the amount of H2 and I2 that's going to convert? That is a cool place in a chemical equilibria called at equilibrium. Okay, all smiles there. You are at equilibrium. Is it still going on? Is it still reactants going to form products and products going to back to form reactants? Yes, it's dynamic. But are the molar concentrations constant? Yes. So that's kind of fun. But the bottom line is, if you were to go at equilibrium and try to snag your product as written, okay, it's not going to be 100% converted from H2I2 because you still got some of those. It just is. Okay. So those are Gen Chem 2 topics, which are kind of fun. We'll actually do some quantification and quantifying. So another reason, those are both reasons you get bias low. Your here in a minute, we're going to call them your lab yields. Your experimental yields are always less than your theoretical yields in those cases. So this is also another reason when something's going on that you don't want it to go on. When you guys did your burning your magnesium ribbon to form magnesium oxide, if you read, I'm sure you did, and you probably had to answer it in your pre-lab questions, but an unwanted chemical reaction at that point was magnesium combining with nitrogen, N2 instead of O2 in the air to form magnesium nitride. Okay? So anyway, you're just not going to, it takes a side road. You're not going to get it all back. Physical losses. Now, there's actually something coming up called gross error. And I will tell you that physical losses do not equal gross error. Sometimes I have students kind of confuse that. Physical losses to me are kind of just, well, take tomorrow's lab. You are going to take copper through, oh my gosh, 5 or 6 different chemical reactions. I guess just 5. But you can take those poor copper atoms through all of these steps. And along the way, kind of inherent in your experiment is kind of transfer issues. Okay? We're going to physically lose some material because it didn't get all the way transferred. So that's an example of a physical loss. Okay? So physical losses, I mentioned transfer error, but oftentimes physical losses are just associated with trying to get it as pure as possible. So for instance, pharmaceuticals, you want them to be, you don't want any foreign molecules in pharmaceuticals, okay? Now there are different ways in chemistry to go ahead and keep isolating, so you purify it, but I bet you guys buy this, that each purification step comes with it a certain amount of loss. Okay, so, all right. So when you guys went from the mass of a reactant to the mass of a product, you were coming up with theoretical yields, okay? So those theoretical yields were if all of that reactant reacted, okay, to form product, and if only the, let's see, there was no other side reactions, and if you were able to isolate all the product. So it's like with the stars aligning, then you can get your theoretical yield is actually what the grams you'll come up with in the lab. So good luck, right? So gross errors are a way that you won't get the right amount too, okay? But gross errors are, just think of them as you did something wrong, out and out wrong, and we all do it, so don't worry about that if you do something wrong. But like for instance, if you, it's not inherent to the design of the experiment, but if you literally like kind of spill something, like Joshua, Joshua.
You can see that in the calculations too.
Okay. You know, and if you, the good example, if you do spill something, make sure you write it down in your lab notebook and include it in your lab notebook.
The percent yield was actually -6 plus or minus 6%, so it should be like less than
Okay.
5.
So but it was attributable to this gross error. Another problem is if you read some volume or some mass wrong, okay, if you record a number wrong, and it happens, but those will be times throughout your experiment, then you won't get the mass you thought you were going to get. That's it. Not following instructions. So this all leads up to a simple ratio. So, and you guys are doing this for your sodium bicarbonate, aren't you, your part 1 calculations. So you could have done it, you did a stoichiometric calculation based upon the mass of sodium bicarbonate, what mass of what, CO2 should you get back? Okay, that was your theoretical yield. Okay, that was a stoichiometric calculation. And then you guys did the subtraction and all that and came up with what you really got. Okay, so what you really got then went in the numerator. Actual yield, sometimes I'll call experimental yield, EXP for experimental yield, and I can't spell yield. Okay, good. It's experimental yield, actual yield, same thing. I had to like look up on PowerPoint how to spell tomorrow because I never know if it's got 1 M or 2. So I looked up, it's just 1 M. So anyway, and then theoretical yield, that's from your stoichiometric calculation. Stoich calc. So yields can only be stoichiometric, how do I say this? Yields are only associated with products. All right, so let's do an example. So in the, I guess it was maybe in part 6, when we did limited supply reactant, or was it, no, it was, I think it was ordinary stoichiometric calculations. Because we said that the P4 was in excess. So a few parts ago, we said that we did this calculation. If you start out with 1.25 grams of Cl2 you should produce and sufficient. Now we know I could also say sufficient or in excess. P4, the other reactant, is in excess. So then we know that we need to do a stoichiometric calculation on our Cl2. We said that you should produce 1.61 grams of PCl3. I think I'm going to start kind of circling that. Okay? So that is your theoretical yield, bottom line. And then this slide goes on to say, well, you didn't get 1.61 back, and it was biased low, which is what we've been talking about. Instead of 1.61, you got 1.08 grams. So then to get the percent yield, all you got to do is a division, and it looks like this. So in the numerator, we put our experimental or actual yield, 1.08 grams. In the denominator, we put what we got with the stoichiometric calculation a few parts ago, which is 1.61 grams of PCl3. Sometimes percent problems, students are like, who needs sig figs? But you need sig figs. So we're still rounding now according to 3 sig figs. So that would be a 67.1% yield. Now, like, say you're out in industry, and processes are known to give certain yields. So you might be thrilled with that, I guess is my point. Or you might think, could have done better. It's all about the numbers. Okay. So these are some problems. We'll take a look at them. These will be due on Friday, Fabulous Friday. And they look like this. So you guys, I don't know if I finished my thought, but you guys got the whole point that oftentimes on the Unit 2 exam in this class, I will include questions about why are your percent yields lower than usual. And it can't be any more obvious than that. In what form will I ask them? I don't know. I haven't decided. Okay. 4.73. You are right there. All right. Looks pretty good. Let's see what I got for my builds. I didn't look at these ahead of time. These are from last semester. So again, I kind of put under the species what it is. Okay. So it looks like we got excess HF. Carbon tetrachloride is in limited supply. The experimental mass of the CCl2 F2 is 187 grams. Okay. So the questions, we have A, B, and C. So for question A, what is the theoretical yield? Theoretical yield then is we're going to go from the limited supply reactant, that 277 grams of CCl4, to question mark grams of CCl2F2. Okay, that's your theoretical yield. That's always a stoichiometric calculation. What's your actual yield? This is a smiley face here. It's that 187 grams. Don't make it harder than it is, right? Okay, I don't know why that question is there unless I'm missing something. And then percent yields is the ratio of those two. It's what you got, 187 divided by what you thought you should get, which is what you calculated in A. Okay, and again, I'll push these out as PDFs. Taking a look at the second one. This one, there's a couple ways, especially to work the last part of this one. So in red, actually, this is a decomposition reaction. So we have a reactant going to form 2 products. So that's your limited supply reactant, the C6H11OH. And notice the actual yield was given in the problem. So the questions are a little bit similar, very similar. A, how are you going to get your theoretical yield? Well, you're going to do an ordinary stoichiometric calculation. Now, stoichiometric calculations are here to stay, so that's kind of why I want to make sure we're all on the same track with regard to doing them. So the next question, what is the percent yield? Okay, same as the C that we just did before, percent yield. It's what you actually got back, which is the 64 divided by your theoretical yield, which is A. And then the C actually is where I've seen students do it different ways, and I'll just kind of show you how I would do it. Again, these are suggestions. You don't have to, sometimes students don't even look at my hints, and sometimes they try to work it and then look at my hints. So anyway, what I did, if you read C, it's kind of standalone question. It says, all right, well, what mass would you have to start with if you knew that, knowing your percent yield, that you would only get a certain amount back and you wanted to produce 100 grams of that product? One of the things I don't like about this problem, there's two 100.0 grams. In fact, I was looking, I'm like, 100.0 grams, there's two of them. So this is just associated with problem C. And so what I did was I just put what I wanted to get back with regard to the product as my first term. And then as my second term, I just went up to the relative amount of the product you got back, which was 64.0 grams, relative to, in the first case, the amount of reactant you started, which was that 100.0 grams. Again, I'm sorry, there's two terms that are 100.0. So I hope those help. But again, that one, there's multiple ways to work that. Okay, so on to solution concentration. Maybe. My slides. And they are. Okay, so solutions. Okay, we are going to talk about how do you say how concentrated your solution is. But before we do that, let's go ahead and say what a solution is. I almost said what a solution is not, but we're just going to say what a solution is. Do you remember in the first unit, we did this whole thing where you have matter, okay, can either be pure, I'll kind of abbreviate this a little bit, or it could be a mixture. Okay, and if it's pure, we had two options. It can be element or compound. Okay, and if it's a mixture, we said that it can be either what, homogeneous or heterogeneous. Homo-G, hetero-G. So what does homogeneous mean?
They're all mixed up.
It's all mixed up, exactly. So solutions are all mixed up. Solutions are basically two or more pure substances that are well mixed. That's a solution. One of my fun things to say is stainless steel is actually an example of a solution. Stainless steel is, you can get different grades of stainless steel that have different amounts of metals that are basically frozen together. Are they homogeneous? Yeah. Are there chemical bonds formed between them? No. Okay. So I think that's kind of fun. But we usually think of liquid solutions. And we think of, there's too many S's to solution chemistry. Okay, I always like the whole beaker thing. So here's my green beaker, okay, my liquid solution. The thing you have a lot of is called the solvent. And the thing that you kind of add a little bit of is called the solute. Okay, now, could you have more than just two things mixed together? Oh, yeah, okay. But usually you have a bunch of something that's your solvent, and sometimes you have multiple solutes that are added. And so if you're kind of thinking solution, there's too many S's. Solution is equal to the solvent plus the solute. Okay, you add them together. All right. So we need to be able to say, to look at a liquid solution and to say how concentrated the solute is, okay? And we're going to focus on two different ways this afternoon. And they are both amount of solute per given amount of solution, okay? There's actually one more that we're going to talk about in Gen Chem 2, starting off, that is the amount of solute per not solution, but per amount of solvent. Okay, and that's the molality. Okay, so these are generic terms. If somebody says that's a concentrated solution of acid, you're like, oh, dude, I think we need to be careful handling it, you know. If it's a dilute solution of acid, you're like, that's probably pretty wimpy. You're right. Okay, so the terms concentrated and dilute you're probably familiar with. So the two ways of describing the amount of solute in a given amount of solution, which is the solute plus the solvent, that I want to talk about are grams of solute per liter of solution. And I'm going to go ahead and unpack that right then, right there. Okay? So if you see G/L, that probably means grams of solute per liter of solution. To unpack that, it would be G solute per L solution. And my abbreviations for solution are SOL apostrophe N. Okay, so that's units unpacked. And the reason we need to unpack them is the whole factor label thing, making our units do what they need to do. That one's not too bad, and this one's not too bad either. We are actually going to run into the second way of saying how concentrated solution is in tomorrow's lab. It's a really common called molarity, and it must have to do something with moles, right? Okay. So, as some of you maybe know, molarity, we use a capital M. Capital M. It is case sensitive because there is something called molality, which again we won't cover until Gen Chem 2. But molarity, bottom line, is moles of solute, so I'll just say moles per MOL/L. And what it really means is moles of solute per liter solution. That's it. How concentrated is the solution? If you have a liter of solution, then how many moles of solute do you have? That's it. Molarity. So let's do a problem in calculating those two. Okay. So for both of these, notice that I have liter of solution in the denominator. One case is grams of solute per liter solution, moles of solute per liter of solution. And I think one of the things we talked about in here is that liters or volume is temperature dependent. Water behaves like other matter when it doesn't change phases, that basically as liquid water heats up, it swells. As liquid water cools down, it contracts. Okay? Now, the crazy thing is when it transitions from a liquid to a solid, it crazily expands. Okay, but as a liquid, it kind of has that thing. So these are temperature dependent. Okay, so let's work a problem, and we're going to knock out how concentrated the sucrose solution is, first in grams of sucrose per liter of solution, and then in moles of sucrose per liters of solution. So I'm all about pictures, right? So somewhere here, I would probably draw a beaker, draw my liquid, draw my arrows. My arrow at the top is usually my solute, which is 32.3 grams. Feel free to abbreviate whatever you want to. You can use the formula or you can use the whole name. I'll just use the whole name. And it says that down here, I'll kind of show my solution down there, and I'll say 225 milliliters. SOL apostrophe N. And then in a picture, I don't even have to look at the words anymore. I can just look at the picture. I guess one more thing, maybe out to the margin, I would say, what is the concentration? So I'd write question mark G, I'm going to even say G S sucrose per L solution. That's it. Well, it seems like all we got to do is take this grams of sucrose and this volume of solution and just do a division, and you're right. Very close. Solution, no pun intended. See the solution to the solution. Okay. So yeah, we simply take that mass of sucrose, and if you want to write sucrose or write C12H22O11, you can do either way, but that's sucrose. 32.3 grams of sucrose divided by 225 milliliters of solution. Now, our question mark was grams of sucrose per liter of solution. So anybody have an idea how we can get the units in the denominator to switch from milliliters to liters?
multiply it by 1,000.
Multiply it by 1,000. Yes. And make sweet. And make sure you put your units there. So Rhonda's right. So the reason we multiply by 1,000 is we have 1,000 milliliters over 1 liter. And now units of liters cancel. Wait, sorry. Units of milliliters cancel. No, I was right the first time. Units of milliliters cancel. And we're left with, final answer, grams per liter, which is awesome. So how do we need to round it? 3. I'm liking it. Very good. Now, sometimes students might say, well, Mrs. Snipes, do I have to write, like, all of that stuff? No, you'd be fine if you just simply wrote 144 G/L at that point. Probably G/grams per liter sucrose. Rhonda's double checking.
Just so I can say, I know how to do it once.
Mhm. Sometimes this makes it more into here. That's why we do homework. Torture. So as you guys can see in your notes, what we're tasked with next is to come up with the same solution. We're going to do molarity. Now, in chemistry, we do this a lot. You're like, dude, if you already knew how to express its concentration one way, why do you even worry about another way? Just because it's fun? So we could do it a couple of different ways. I'm going to piggyback on this, okay? But if I piggyback on 144 grams sucrose per 1 liter of solution, and I'll put my question mark up here. What is the molarity? Sometimes to me it helps to actually, what are the units of molarity? Well, they are going to be mole sucrose per liter of solution. So that's my target. That's my question mark. So somehow all I got to do is convert from grams in the numerator to moles. And how do we go from grams to moles?
We use the molar mass.
We use the molar mass. Exactly. Exactly. So somewhere in your work you would need to show this. This is the molar mass of sucrose. We take 12 times 12.01 for carbon plus 22 hydrogens times 1.008 plus the term for oxygen, 11 times 16.00. Rounding it to 2 decimals, we get 342.30 grams per mole. That means 342.30 grams sucrose, oh my goodness, per 1 mole sucrose. Okay? So let's see, I want grams to cancel. I want to be left with moles. Seems like I need to flip that thing. So this was the concentration in grams of sucrose per liter of solution. Now if we use the molar mass, the flipped version of the molar mass, 1 mole of sucrose over 342.30 grams sucrose. Now my grams of sucrose cancel. I'm left with moles of sucrose, units, moles of sucrose per liter solution, which is perfect. Round to 3 significant figures. Okay, 3 significant figures, I got a value of 0.419. That's not what you got, Mike? Okay.
I got a .421.
Yeah, that's what I got.
Oh, I wonder if I used my non-rounded version. I don't have my calculator here. I'll try to remember to look into it, so it sounds like you guys are on the right track. So 421?
Yeah, that's what.
Thank you. Okay.
My calculator's wonky, though, see every.
Do you guys have the same calculator now? No. Okay, I'll try to double check what that is. I think might just be an out and out rare, but hopefully we're on the same page. Okay. Good job. Okay, one more problem. So that movie's not going to play for us, but these still images will play. So a lot of times, well, I was going to say, if you're into lab work, a lot of times you will have to make up your own solutions. And oftentimes we use volumetric flasks to make up known concentrations. Remember, the volumetric flasks are kind of like your pipettes, in which they have just one calibration mark, at least the pipettes that you guys have used so far. And so in this case, the target was 0.250 molar potassium chromate. And so they did the math and they said, well, if I want 250 milliliters of solution, I'm going to have to weigh out 12.1 grams of the solid potassium chromate. So they have added their solute in here, okay? So it's not really a trick, but in order to get room for agitation, physical agitation, you don't want to fill it up right away. If you have your solid in there, you want to leave some kind of swishing room, and that's kind of what the middle one is. Okay, and once it's all dissolved, and things dissolve at different rates, once it's all dissolved, then you're ready to go ahead and fill it up to the line, which is that last one. So, all right, we got it in us. One more problem. And it's not as straightforward as the sucrose problem, okay? Darn it. Okay, we have the term salt just means ionic compound. So we have some sort of ionic compound. Actually, it's a hydrated salt. It's, we've talked about waters of hydration, okay? Now, one of the things about those waters of hydration, and I'm sorry I'm smiling because I do think it's adorable, is that when you take this guy, okay, and you add water, okay, I'll just put water here, okay, it basically breaks apart and you get the nickel 2 chloride, AQ, aqueous, it's dissolved. Those waters of hydration just go float around like those other waters that were already there that you dissolved them in. That's how a hydrated salt works. I think that is so cool. Makes sense. So if you read it a few times, let's go ahead and draw a picture. We're stalling, right? I'm going to go ahead and make a volumetric flask instead of a beaker. My beakers are bad, but my volumetric flasks are even worse. Okay, so here's my mark on my volumetric flask. To that line is kind of like the volumetric flask we looked at before. 250.0 milliliters. That's the capacity once I filled it to the line. And the problem says I am going to add 8.320 grams of my hydrated salt, NiCl2.6H2O, okay? And then just like kind of like you saw before, after I add my solid down here, I'm going to add water to ultimately dissolve that up and make that. So my solution volume, I'll go ahead and put kind of a brackets over here on the left. My solution volume is, let's see, I'll put SOLN is equal to 250.0 milliliters. 4 sig figs there, right? So that's what we got going on. And it is kind of like the sucrose where we're after what is the grams of nickel 2 chloride per liter of solution. Okay, what is the moles of nickel 2 chloride per liter of solution? Again, those water hydrations are kind of a pain in the butt, but that's kind of the way chemistry is sometimes. Now, I'm going to start with B first. So I'll kind of show you what that looks like. So kind of background info, looks like you already have these. Okay, what's going to help us kind of along the way is what is the molar mass of just the, remember we call that anhydrous. NiCl2 without the .6H2O, that is anhydrous. Okay, down here, we would call the hydrated stuff the hydrated stuff. Anyway, the molar masses of everything. That's going to help us. And you'll see why here in a minute. So here we go. We're going to go for B first. Do you have to go for B first? No. Are there different ways to work this? Yes. Is that your problem? No, that's mine. Okay. So what I would do is kind of like we did before. I would take the mass, in this case, of the hydrated salt, the whole enchilada, the 8.320 grams of NiCl2.6H2O, and I would divide that, or wait a minute, no, I'm not. And I would go, I would try to knock out moles of the anhydrate, the NiCl2. So I would put that term over 1. I would put that simply over 1. My next term is the molar mass of the hydrated salt. So 1 mole of NiCl2.6H2O over 237.69 grams of NiCl2.6H2O. Now, the units of grams will cancel. That will leave me with moles of the hydrated salt. How many moles of nickel 2 chloride are there in 1 mole of nickel 2 chloride hexahydrate? Trick question? I saw a finger go up. 1. I agree. And that's actually my next term. So now if I just put 1 mole of NiCl2, the anhydrous, per or over 1 mole of NiCl2.6H2O, the moles of NiCl2.6H2O cancel. We're left with moles of NiCl2. Now I'm doing this in steps. So actually I'm ready to go ahead and resolve this issue. Okay, so it looks like we need to round. Wow, how many sig figs we get?
4.
I'm thinking 4. Dang, that's exciting times there. 4 significant figures. That'll give you 0.03500, and the units of that would be moles of NiCl2.
Why would we, for the molar mass of the hydrate, why would you multiply it by 6?
You would need 6 waters of hydration. You mean like on the previous slide? Okay, let me come back here and see what the previous slide said.
Like, I thought this was or is this completely different?
Yeah, this one, the 18.02 is 1 water, and you need 6 waters.
Okay.
So, yeah. That's not as clean as it actually could be. It should be, no, but that's okay. But I think we're on the same page, right? Okay. So now to get to molarity, which is B, I just take moles divided by the solution volume. So I'm ready to take that and divide it by my 250.0 milliliters of solution. So 0.03500 moles NiCl2 divided by 25.0 milliliters solution. And we're kind of like where we were before, where this isn't molarity because this is moles per milliliter instead of moles per liter, so we need to multiply by 1,000, don't we? So if we introduce a term of 1,000 milliliters over 1 liter, then our milliliters will cancel, and we're left with moles of NiCl2 per liter of solution, which is perfect. So now maybe you'll see why for the volume of the volumetric flask we went with 250.04 sig figs, because we don't want our glassware to limit, we want it to be as free as possible, because we had 4 sig figs. So we're still rounding according to 4 significant figures is my point. So I got a point, your calculator I think would just flat out display, I think, 0.14. Shelby's doing it back there. But you need 4 significant figures. And actually this down here, this actually is how I would write it. 0.1400, big M, molarity, NiCl2. So as was the case before, I'm gonna piggyback on that. That's moles of NiCl2 per liter of solution, and the A says grams per liter solution. So bada boom, if I go ahead and introduce the molar mass of NiCl2, which from a few slides ago, we said the molar mass of the anhydrous salt was 129.59 grams per mole. Now I have 0.140 moles NiCl2 per 1 liter of solution times 129.59 grams of NiCl2 over 1 mole of NiCl2. Moles will cancel, and we're left with units of grams of NiCl2 per liter of solution, which is wonderful. Looks like we're limited to 4 significant figures because of the first term. So I get 18.14 grams. And like I said, I might even just kind of do 18.14 G/L. But I probably would say NiCl2. So that bumps up against another assignment slide. So let's go ahead and take a quick look. But these will also be due on Fabulous Friday. And we'll take a look at that alternate method when we come back. But so
What's today's date?
the 5th for Joshua. 4:33. Yeah, it looks like this one. And I didn't look at these ahead of time, so just bear with me. I would draw a picture. Okay. Looks like we have 3 different solutions. You're like, oh, direct. So we have 3 parts to this one question. Here's the picture that goes along with A. Okay, and again, I'm just going to push these out. Some of these are not as hard as others. I guess that's just kind of how it goes. There's A, there's B. B is a little interesting because it's not pure, so you have to take that into consideration. My hints kind of tell you how to do that. Oop. And then C down here is probably the most interesting. And C gives you the density of the solution. Okay. Let's see. I'm trying to think. If you just want to do A and B and then hold off on C until Monday if you want to. Because C hurts my brain right now. It's very doable though. The next one, similar to, similar. So it looks like if you want to skip 34B and what was that, 33C, you can. But they will be due on Monday then. They just involve density. So we've definitely, I'm not going to tell you anything new, but we'll take a look at C and B for hints on Friday. Okay, any questions? They're all fun. Good luck. Okay.